Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about the solubility product constant. It's a three-part video series. This will be part number one. And basically, in part number one, I'd like to talk about what does it mean to be a low solubility solid and be placed in water. Part number two, I'd like to talk about if you know the solubility, can you calculate the value of the equilibrium constant, KSP? And in the third part, I'd like to talk about if you know the KSP, are you able to calculate the solubility of the solid? Okay, so there's three parts. It covers the whole topic. So for this one here, what I'd like to talk about is low solubility solids. Okay, in any other part of chemistry, when we talk about taking an ionic compound and dissolving it in water, we either say that it's aqueous because it dissolves, or we say that it's a solid because it doesn't dissolve. Right, so let's say you have a beaker of water and you have like a spoonful of sodium chloride, salt, and you throw it into the water. Sodium chloride loves water, so it dissolves really well. So if you put sodium chloride into water, you're going to end up with salt water, sodium chloride solution, and we would say that it's aqueous, right? It dissolves really well. If you put something like silver chloride into water, so you have a spoonful of silver chloride, you put it in the water, what you'll find is that it hits the water, it'll sink all the way to the bottom, and then it just sits there, right? It does not appear to dissolve at all. And we would call that a low solubility or insoluble solid. And so in the world of chemistry, we would just say that it's silver chloride, we put a little S behind it, say it's solid, to indicate that it doesn't dissolve easily. Now, for this specific part of chemistry, what we want to do is we want to talk about what really happens to these solids when you throw them in water, right? You throw them in, the majority of it settles to the bottom, but it's not 100% insoluble. Okay, there is a very small amount of that silver chloride that will actually dissolve and break up in water. So that's the kind of things that we want to talk about when we talk about solubility product constants. Okay? So when we talk about ionic compounds, in reality, they all dissolve somewhat. Now, there's a few that they dissolve so little that you'd hardly even notice it. Okay? And the silver chloride would be one of them. And I've got a couple of pictures here to kind of describe what's happening. If you have silver chloride as a solid, it forms a very nice, very organized ionic compound. So this would be like silver pluses, chloride minus, silver plus, chloride minus, silver plus, chloride minus. It's very well organized. It alternates between positive and negative ions. Now, if you throw this into the water, what the water molecules do is the water molecules wedge themselves in between the ions. So this little water molecule is going to attempt to wedge itself between the silver plus and the chloride minus. Now, if a substance dissolves really well, that means the water is very effective, very good at wedging itself in and splitting the ions apart. If you have something that is very low solubility, then the water has a very difficult time wedging these ions apart. So for the silver chloride, the water will get in, it will force a few of these ions to separate out and become dissolved, but not all of them. Turns out very few of them are actually forced apart and forced to dissolve. Now this is an equilibrium. As you break them apart and free them, so that way they become dissolved, some of the ones that are dissolved will come back and reform solid. That's the equilibrium part, right? There will be some that are breaking free. Simultaneously, there will be some that are reattaching themselves to the solid. So when we write this equation, we like to say in the beginning, we started off with the solid. There's silver chloride solid. Here it is. And we like to say that some of it breaks up. And when you break up, you become silver 1 plus, Cl1 minus, silver 1 plus, Cl minus, right? When your water gets in between the ions and forces them apart, you're now just a silver plus all by itself, completely surrounded by water. Or you're a Cl minus, all by itself, surrounded by water. So we write these equilibriums as the solid breaking up into the ions, right? Silver chloride is made up of silver 1 plus ions and Cl1 minus ions. And when they've split up and are surrounded by water, they are now aqueous. If you're going to be doing a problem that involves solubility product constants, your first step will always be write the equilibrium. Show how the solid is going to break up into the ions. Okay, so let's talk a few other things here. When I write silver chloride solid in equilibrium silver plus aqueous and chloride minus aqueous, this thing is called my equilibrium. When I write my K, my equilibrium constant equals products divided by reactants, that's going to give me an equilibrium expression. Okay, so you have to get the terminology down. This is the equilibrium. It shows the reactants, it shows the products. It shows reactants turning into products, it shows products turning back into reactants. When we talk about the equilibrium expression, this is the calculation that will allow us to calculate the value of KSP or the value of the concentrations. Now, I do have other videos that talk about homogeneous and heterogeneous equilibrium expressions. If you're finding that this is perhaps giving you a little bit of trouble, you might want to pause here, go back and take a look at especially the heterogeneous equilibrium expression, and then come back. And the reason why I suggest the heterogeneous equilibrium expression is because this is a heterogeneous equilibrium. You have both solids and aqueuses, right? Heterogeneous means you have a mixture of solid, liquid, gas, or aqueous. If this was a homogeneous equilibrium, they would all be aqueous or they'd all be gases. They'd all be the same, okay? Now, the reason why I say you might want to go back is because if you're going to do an equilibrium expression, it's always the equilibrium constant, K, equal to the products divided by the reactants. And in the heterogeneous equilibrium expression video, I do talk about how if you have a pure solid or if you have a pure liquid, they don't appear in the expression. And that's the reason why there is no denominator here, right? Because really, there should be a denominator with the reactant. So if I look at my products, I've got a silver plus, so I wrote down silver plus. An equilibrium expression is all about concentrations, right? I want to know the concentration of the silver and the concentration of the chloride. And that's what the square brackets are telling me. So the square brackets here are telling me concentration. There are powers, because there's a 1 used to balance this equation in front of the silver. This is actually silver to the power of 1. When I balance this equation, because there's 1 chloride, the power here is 1. So that's my reactants. My products. My two products, both as concentrations, square brackets, using the numbers that balanced it as powers. Now my reactant should be in the denominator. So this reactant should be down here. I should write silver chloride, put it in square brackets. Because there's 1 of them, put a power of 1, right? That should be there. But because my only reactant is a solid, I get to leave it out. It just doesn't appear. And if you have nothing to put on the denominator, technically it's a 1. Okay, and again, the video on heterogeneous equilibrium expressions does go over this in a much thorough method. So if you are feeling a little lost, you might want to go back. And if you have a denominator of 1, you don't have to write it down, so we just write it as Ag plus times Cl minus. Power of 1, power of 1. Now, this is an equilibrium, but it is a very specific type of equilibrium. So instead of just calling it K, I'm going to call it KSP, right? It's like when you give something a special name, because you could talk about like your pants. Okay, you have a whole lot of pants. You got shorts, you got jeans, you got dress pants, you got a whole lot of pants. Pants is like the general term. Equilibrium constant, kind of the general term. But if you wanted to talk about a specific type of pants, right? These are my shorts, or these are my jeans. That's what we're doing here with the KSP. We're talking about a very specific type of equilibrium. And the very specific type is that we're going to have something that really doesn't like to dissolve in water, and we're going to consider what happens when you put it in water and the very small amount actually splits up and dissolves, right? We're going to talk about things that are insoluble. And insoluble is in quotation marks because it's not truly insoluble, it's just mostly insoluble, okay? Now, KSP stands for Solubility Product Constant. Now, the reason why the word product is in its name is because if you look at this thing, right, this is supposed to be a quotient. You're supposed to have products on the top, reactants on the bottom. But for this kind of reaction, your reactant will always be a solid. Okay, the reactant will always be a solid, which means the reactant will always be left out, which means you'll never have a denominator. So instead of it being a quotient, what does it look like? It looks like a product. You've got something times something else, right? And that's unique. It's very rare for your reactants to cancel out and your denominator to go away. That's why it's part of the name. The other reason why we have solubility here, or the other part of the name is solubility, is because this whole thing is about trying to get a handle on dissolving things that don't dissolve very much. And if you're going to be dissolving something, that's solubility, right? You're soluble, dissolving. So we do like to call this one our solubility product constant, and we give it the symbol KSP. And it is purely for equilibriums where you have a solid that doesn't like to dissolve, and you consider what's happening as it does dissolve, the little tiny bit that it will. Okay? Now, this is another point here that you should probably put in your memory somewhere. The bigger the value of K, the better the substance is at dissolving. Now, when we get to a few problems in video number 2 and video number 3, you're going to find these KSPs are tiny, like ridiculously tiny. But even though they're very tiny, you can order them from the tiniest tiny to the biggest tiny, right? They're all small, but you can rank them from smallest to biggest. The biggest ones will have the most solubility. The smallest KSPs will have the lowest solubility. Okay, so this is my equilibrium. This is my equilibrium expression. And in order to do these problems, you are going to have to write both. Step number 1 is going to involve writing out the equilibrium, and then step number 2 is going to be writing out your equilibrium expression. So let's take a few practice problems at that. So it says, please write the equilibrium expression for each of the following low solubility solids dissolving in water. Now you will notice that it does not say you need to write out the equilibrium. It just says you have to write out the equilibrium expression, right? The equilibrium expression. Now, you come back here. It's very hard to write out an equilibrium expression if you don't have an equilibrium to build it from, right? Products go on the top. Reactants go on the bottom. If you don't know what the equilibrium is, it becomes very hard to write the expression. So even though this problem does not ask you to write out the equilibrium, that's your first step. Okay, so if we take a look at our lead 2 sulfide, so PbS solid, it is going to be an equilibrium. If you throw lead 2 sulfide in water, the vast majority of it will settle to the bottom and just sit there. But a very, very tiny amount will break up to form ions. So what 2 ions do you have in lead 2 sulfide? You got some leads and you got some sulfides, right? Lead sulfide breaks up to give me lead and sulfide. When they break up, they started as a solid, but now they're both going to be aqueous. Now there are 2 important things that you have to worry about. You have to make sure that this is a balanced equation. If you start it with 1 lead, you have to end with 1 lead. If you start it with 1 sulfur, you have to end with 1 sulfur. You have to make sure that it is balanced. Okay, balancing is very important. When we get down to some of these later problems, you can see that this has 2 silvers, this has 3 strontiums, right? You're going to have more than one of things. So you have to make sure it's balanced. I did start us on purpose with a nicer example that went with 1 lead to 1 lead, 1 sulfur to 1 sulfur. This is already balanced. The other thing that you have to worry about is when these things split up and they form ions, they each have a charge. So you are going to have to be able to figure out the charges on these. Now, if you are finding that writing the charges is giving you a little bit of trouble, I do have a video that talks about how you figure out the charge on ions based on the periodic table. I'll put a link to the video in the description. So that way, if you're having a little bit of trouble figuring out what the charges are, you can refresh your memory. Okay, so if you go to your periodic table, sulfur is in column number 6. If you're in column number 6, your charge is going to be a 2-. Now, your lead is one of the exceptions to the multivalent ion rule. Okay, if you think back, transition metals in the middle of the periodic table can have more than one charge, so they have to use Roman numerals. So if you're talking iron, iron can have a 2 charge or a 3 charge. So you have to talk about like iron 2 versus iron 3. Lead is not a transition metal. It's slightly farther over on the periodic table, but it also can have more than one possible charge. Lead can be 2+ or 4+. Okay, so it can be multivalent. And what you have to decide is, do I have the 2+ version or do I have the 4+ version? And the easiest way to do that is based on the charge of its partner. Because when you put ions together, the total amount of positive has got to match the total amount of negative. So if you've only got 1 lead and 1 sulfur, right? 1 lead, 1 sulfur. And you know the total amount of negative charge is -2, then the total amount of positive charge will have to be a +2 to balance it. That's how you know it's lead 2+ and not lead 4+. Okay? So again, if you're having a bit of trouble with figuring out the charges, take a look at my video that I've linked below and review how do you find the charges on ions. Now, we're down to our equilibrium expression. And those are pretty easy, right? We are going to put products on the top, and we are going to put reactants on the bottom. So my first product is a lead 2+. So let's put in a lead 2+. Now, these problems are all about concentration, right? Because you could know a lot about the lead 2+. You could know its density or its mass or its volume. You could know a lot of things. But the one thing that I want to be able to know and use is concentration. And the way that we tell everybody that it's concentration is square brackets. Okay? Now, when we balance this, we didn't really put any numbers in. But if you don't put any numbers in, it's really ones, right? For every 1 lead sulfate, you get 1 lead and 1 sulfur. The numbers that were used to balance the equation, those are your powers. So that's really to the power of 1. The second product is an S2-. So let's put in our S2-. Again, to show that it is concentration, we are going to use square brackets. And again, you use the 1 to balance this equation in front of the sulfur, so its power is going to be a 1. In the denominator, that's where I would put my reactants. But my reactant is a solid, and I'm not allowed to include solids. So really, it's just over 1. Now, in the world of math, do you need to write down a denominator if the denominator is just a 1? No. So if you wanted to, you could rewrite this as KEQ equals the concentration of lead 2+ times the concentration of sulfur 2-. And I also left out the powers of 1, because if you've got something to the power of 1, you don't need to write the 1. Now, the last thing that I should probably point out here is in the original equation, the 2 products were added, right? I have lead 2+ plus sulfur 2-. But in my equilibrium expression, they are multiplied. So these are times. Okay, so you're added into equilibrium, but you're multiplied in the expression. And what we now have is our equilibrium expression for taking some lead sulfide, throwing it in water, and attempting to dissolve it. All right, try the next one. You're going to take some barium hydroxide. Barium hydroxide. Barium hydroxide hates water. But you're going to throw it in water anyway. The majority of it will sink to the bottom of your beaker as a lump of solid, but a little tiny bit of it will split up and form an aqueous solution. So let's show our equilibrium and let's split it up. Now these things only ever split into two pieces. So if I look at this, I have a barium and a hydroxide. So I'm going to get bariums and hydroxides. Okay, they only ever split into two. You started off as a solid, but you do end up as aqueous, so aqueous and aqueous. Now the two things that you have to be careful of. You need to balance it and you need to put in the right charges. So if I look at this, I have one barium at the beginning, I have one barium at the end. That's good. But if I look here, I don't have one hydroxide, right? Here's my hydroxide. I have two of them. There's two hydroxides. Now, I don't leave that 2 as a subscript. I am going to put the 2 out in front and say I have 2 hydroxides. Okay? Now, the last thing you need to do is your charges. So if you go to your periodic table, barium is in group 2A. If it's in group 2A, that means your charge is a +2. Your hydroxide is a polyatomic ion, right? It's made up of an oxygen and a hydrogen together, so it's a group. So if you go to your polyatomic ion table, you can look it up and see that the charge is -1. Now, I'm feeling very happy here because the total amount of positive and the total amount of negative balance. Because the barium hydroxide has 2 positives, each hydroxide has 1 negative, but there's 2 of them, right? You got 2. So a total of 2 negatives going with your 2 positives and a cancel. In these problems, this is going to be your hardest step. Right? Writing your equilibrium expression is relatively straightforward, but making sure you get this original equilibrium correct, that's what's going to give you some trouble. So if we do write our equilibrium expression, it is KSP, and over here I put in KEQ, because when you're talking just a general equilibriums are often just called Ks, or KEQ for just equilibrium. So for this one, I apologize, I should have called it KSP, because this isn't just any old equilibrium, this is a special equilibrium. And if it's a special equilibrium, it should have a special name, right? So it is KSP. Okay, so now let's see if we can streamline this a little bit. I know that I should be thinking products in the numerator and reactants in the denominator. But for every single one of these, my reactant is going to be a solid. Okay, that's the defining part of this problem. So I am never going to have a denominator, ever. So let's do my numerator, let's do my products, and I'm not even going to draw my line because I know there's going to be nothing in my denominator. So my first product is barium 2+. I put square brackets around it to emphasize the fact that it's a concentration. And when I balance this equation, really, I talked about having one of those and one of those, right? If you don't have a number in front, it's a 1. So this would be barium 2+, and because there's one of them, I'm going to go power of 1. My second product is a hydroxide. Square brackets around it to say that it's concentration. And when I balanced this thing, I balanced it and showed that there was 2. Because there are 2 of them, this is going to be squared, right? Whatever numbers you use to balance becomes your powers. Now, that's my 2 products. At this point, I should be drawing my line and talking about my denominator, but my only reactant is a solid, and if you've got a solid, you don't count it. And if you have nothing to put in your denominator, it should be a 1, right? So this really should be over 1, but I know that if I put it over 1, I can cancel that out, so I'm not even going to do it. And the last thing, in the original equation, the 2 products were added, but in the equilibrium expression, they are multiplied. So KSP would be barium 2 plus to the power of 1 times hydroxide minus to the power of 2. Okay, let's try a third one. So if I have silver 2 CO3 solid in equilibrium. Now the best way to figure out how these are going to split up is figure out what their name is. Like if I look at this, Ag, that's silver. If I look at the CO3, right, the CO3 is a group, it's a polyatomic. The C, the O, and the 3 all come together, and that forms carbonate. Right, so if I were to name this thing would be a silver carbonate, which means the two pieces, when I split it up, are going to be silvers and carbonates. So I'm going to get silvers, and I'm going to get carbonates. Okay, they only ever split into two pieces. When they split up, they do become aqueous, so these are both aqueous. Now, the two things I need to do, you have to balance the equation, and you have to tell me the charges. So if we talk about balancing this thing, when I had them together, here's my silver. The little 2 next to the silver tells me that there's 2 of them. So that means I have 2 silvers. The C, the O, and the 3 are all part of the same thing, right? This unit is carbon and 3 oxygens. How many CO3 groups do you have? You just have one of them. There's only one CO3 group, one CO3. All right, if we talk charges, the carbonate is the easier of the two, because if you go to your table of polyatomics and you just look up CO3, if you look up carbonate, it'll tell you that the charge is -2. Now the silver is a transition metal. And if you've got a transition metal, they're very difficult to predict what the charges are. Now, the silver actually is an exception, right? If you think back to your periodic table and you think to the transition metals that are in the middle, there are only 2 that don't use Roman numerals. There's only 2 that don't have multiple charges. Silver and zinc. They're the only 2. The only charge that a silver can have is +1. And I've got to say, when we're talking about these low solubility products, silver 1+ is one of our favorites. Okay, it shows up a lot. So it is worth your while memorizing that silver is always a +1. It's an exception in the transition metal world because pretty much all the rest have more than one possible charge, right? Iron can be 2+ or 3+. But a silver can only be +1, right? It is an exception, and it's one that you should know. Now, if you want to check to make sure everything worked out all right, what's the total amount of negative charge? I have 1, 2 minus. So I got 2 minuses. How many +1s do I have? I have 2 of them. I have 2 +1s. So +2, -2, they cancel out. We're good. This, like I say, is the hardest part. Once you have this written down correctly, writing down your KSP, much easier. Because all you have to do is tell me what is the first product, silver 1+, put square brackets around it to say that that's the concentration, and then whatever number you use to balance this becomes the powers, that's squared. Then you tell me what the second product is. Second product is CO3 2-. Put square brackets around it to tell me concentration, and then you use whatever number out in front was used to balance it as your power. These were added in the equilibrium, so they are multiplied in the expression. The denominator should be my reactant, right? I should have something over the denominator, but my reactant is a solid, so it gets left out. And if it gets left out, it becomes just a 1, and we can ignore it, right? The KSPs are quite easy to write once you've got the equation. All right, let's take a look at the last one. Last one is a strontium phosphate. Sr is strontium, and PO4 is a phosphate. Just its name tells you what the two pieces are going to be, right? When I split this up, I'm going to get strontiums and I'm going to get phosphates. Okay, so let's put a little line here so that way we can separate them out. So this would be an SR3PO4 twice solid. When you throw it in water, a very small amount of it will split up. And like I say, it's going to give you strontiums and phosphates. Strontiums and phosphates. Strontium is SR. Phosphate is PO4. SR, PO4. When you break them up, they do become aqueous. So aqueous and aqueous. And now you have to tell me how many to balance it. And then you have to tell me the charges. So if I look at this here. Here's my strontium. How many strontiums did I have? 3. Here's my phosphate. Here's my PO4. How many phosphates do I have? 2. So I have 3 strontiums and 2 phosphates, right? Little 3 next to strontium tells me I got 3 of them. A little 2 next to the phosphate tells me I got 2 of those. Now, if you go and you look up charges, strontium is in group number 2A. So strontium has 2 positive charge. And phosphate is a polyatomic ion. So if you go to your polyatomic ions table, this is a 3 minus. Now let's make sure our charge is balanced. If you have 3 2 positives, 3 times 2 gives me 6 positives. And if you have 2 3 negatives, right? Each one of these is a 3 minus, but you got 2 of them. 2 times 3 is 6 minus. So 6 positives, 6 negatives, they balance your good. Okay, let's talk about our KSP. So KSP is first product, strontium 2+. Put it in a square bracket to show concentration. And because when you balanced it, you put a 3 in front of the strontium, this becomes power of 3. Second product, PO4, 3 minus. You put it in square brackets to tell me that it's concentration. And when you balanced it, you put a 2 in front. So that's going to be power of 2. The denominator should be the reactant. The only reactant I have is solid. Solids don't count, so I have no denominator. Although the 2 products were added in the equilibrium, they are multiplied in the equilibrium expression. Now, for any problem that you're going to do that involves KSPs, solubility product constants, the first 2 steps are always going to be the same. The first step is going to be please write your equilibrium. Now, it's likely that if you're doing worksheets or practice problems on these, that the first few may actually write out the equilibrium for you. But more likely is it'll be just like this. It'll tell you what the solid is and expect you to be able to predict what the products are. The second step will always be writing KSP equals. Okay, so you'll have to do your KSP equals. The next step, of course, now is once you have this equation, is either someone will give you the concentrations and ask you to find the K, or they'll give you the K and ask for the concentrations, right? Because this is an equation. It's kind of like in math class now. Give you one thing, ask you for the other. So in part 2 of this 3-part series, I will give you concentrations and ask for K. And in part 3, I will give you the K and ask for the concentrations, which is a little bit harder. That's why I left it to the last part of the series. So as always, I'd like to thank you for joining me here at Chemistry with Dr. Clark.